Good evening. Shortly, we will hear an interesting lecture by Dr. Ya'akov Glik on recent advance in high-power brightness enhancing Raman fiber lasers. This is part of webinar series organized by Photonics Israel on various aspects of photonics. The photonics industry is a technological and economic growth engine in the world. In Israel, it contributes about $6 billion annually to the economy. Photonics Israel operates within Engineers Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with its photonics entities in the world. We are open to your suggestions and would love to help foster new local and international collaboration. My name is Shlomo Glaser. I am the manager of Photonics Israel. Dr. Ya'akov Glik is a research physicist in the Applied Physics Division at SOEC NRC, Yavne, Israel. He has headed the fiber laser group in the laser department. Dr. Glik, the stage is yours.
Ready to go?
Yes.
Okay. Okay, good afternoon. My name is Ya'akov Glik, and I'd like to talk to you about the latest developments in high-power Raman fiber lasers with brightness enhancement. And this is a little bit of a long title, so I'll try to break it up into a few pieces. First of all, by speaking about giving you a short introduction to some laser applications. I'm sure most of you or many of you are familiar with them, but I'd just like to point out some applications. And then I'd like to go into the direction of why fiber lasers for these high power applications. Once we've covered that territory and we're talking about lasers and then fiber lasers, I want to talk to you about the motivation for using Raman fiber lasers. And that's going to be most of the talk. And we're going to talk about various Raman laser configurations, Raman fiber laser results. And then finally, I'm going to talk about directions and challenges for reaching multi-kilowatt lasers using Raman fiber lasers. So first of all, just a quick introduction of what is a laser as opposed to a beam of a flashlight. I'm sure most of you know that a beam of a flashlight diverges very quickly. On the other hand, the laser has high power. It can be tightly focused. And most important, it gives the ability to transfer high power to a long distance, that as opposed to a flashlight beam. So that's the advantage of a laser. And now the question is, what are the things that we can do with the laser? And here are a number of applications that lasers can be used for. And let me again point out that this is not necessarily fiber lasers. These are any kind of lasers. So for example, in defense, there are many applications of sensing. For example, range finding. Many vehicles that want to know how far away the target is have to use range finding to measure the distance. That can be done with lasers. Fire control for sharpshooters, and there's wind sensing, which is also something which is important for defense to know the wind direction. Detection of chemical hazards. If there's a chemical hazard at a distance, one can use lasers in a spectroscopic sort of a application to teach us what sort of chemicals might be in that distance that we're looking at. Another application is explosive detections from a few tens of meters, also spectroscopically. By laser-induced fluorescence, we can learn about the chemicals that might be in something which is suspected as an explosive, and then we can also, and then that's another possibility of actually using it to cause the explosion to occur. Another thing is designation and guidance. Lasers can be used to point at targets, and as I'm sure you know, the laser beam can be used by missiles to guide them to the target. There are also quite a few countermeasures that should be considered also with lasers. Talking about one possibility is to blind sensors. if we're trying to knock out an enemy sensor, that's something that can be done with a laser. And if you look at the bottom axis here, you'll see powers that are, let me just get this arrow here so that I can show it to you, right? The powers that are required for each one of these things. And here we're talking about in the orders of kilowatts and 10 kilowatts, 100 kilowatts, megawatt. These are all kinds of powers of lasers which may be required for each of these applications. We're talking about, so at the low power level, we're talking about blinding sensors, about detonating landmines, other sort of disabling ground-based radars. And then as we increase the power, we're talking about disabling harder targets. For example, in-flight artillery rockets or soft UAVs at long range. These are the kind of things that one would like to do with lasers, and these are the powers that are believed to be required for these types of applications. So now this is in terms of defense. Well, of course, there's another thing which is showed here in the picture: aviation protection against missiles. Lasers can be used on aircraft to cause the missiles that are shot towards the aircraft to miss the target. So that's another defense application. But there are also many applications in industry. For example, material processing, welding, drilling, marking, brazing, micro machining. These are all things. Here are some examples on the bottom right. You can see of things that were done with lasers. For example, the manufacture of stent. You see the accuracy in the cutting of this object benefits from the accuracy of a laser. And of course, there's also lasers which are used in communication, of course, which you're all familiar with, optical communications, which use lasers. So this was an example. This was just a quick list of things that can be done with lasers. And now I want to tell you about. I want to emphasize a little bit about material processing with lasers. I talked about lasers, but I want to try to convince you. One moment. Sorry about that. I want to try to convince you that lasers are good, but it's also very important to have a high beam quality in order to get to give you an advantage for material processing. Here on the left, you can see a picture of a material processing with a laser, where you see the laser is cutting or maybe welding this piece of metal, and here I show you another picture of a plate, a metal plate, where in this case there were 100 holes were cut with a laser. Now I want to ask you a question, whether you know, you don't have to answer. This is just a rhetorical question, of course. How much time was one thing that it would take to cut these 100 holes with a laser? And now, Yaniv, can you please run the first video? Okay, here we're going to see some cutting with it. Now we're going to see these holes that are being cut with a laser. You may have seen that it took about 1 second, but now the video is going to be slowed down to 1/8 of the actual speed, and you see the second cutting now. And now in the moment you'll see the first cutting. This is this is a 1/8 of the speed, so you can see that whole thing took. Here it takes about 10 seconds after it, so it took about 1 second to cut all those holes. And now the question is, we went out here. The question is, why should it take? How is the cutting able to work so quickly? And for that, Yaniv, please show the second video. Okay, now, 1 second. Okay, now, what I want you to notice here. Maybe we're going to run this video again. I want you to notice is how, Yaniv, we're going to run this video again. You can notice how far away the laser is from the product. You see, it's about 1 meter away. And the reason that can be done is because this laser has excellent quality, and it allows the laser to be pointed from such a distance to do this material processing. Now we're going to go back to the Okay, you can stop the video now. We're going to go back. Let's see if we can share the screen again. Okay, now we're going back to the presentation. Okay, so you can see, if you look at the top picture, you see how close the laser is to the work point, and in such a case, to move something as heavy as that quickly, it's impossible. So the advantage of having an excellent beam quality is the fact that you can work from a distance and you can move the beam so quickly without having to maneuver the heavy laser head at such high speeds. You slightly change the angle of that, and that gives you the effect and allows you to cut at the correct speed. Of course, you need the high power. So again, if you're looking for a good laser for applications, you need something which is high power and excellent beam quality to allow you to process at a distance or at a large distance. Okay, so now that was my quick introduction to some applications. So I hope to have convinced you that high power lasers have many applications with a preference to excellent beam quality in order to keep the power density at a distance. But the next question is, why fiber lasers? Like I said, any laser can do that. There are many other types of lasers, which I'm sure many of you are familiar with. There are gas lasers, such as helium neon lasers, and CO2 lasers, argon lasers. There are solid state lasers, neodymium YAG, ruby. There are diode lasers. You're sure all of you are familiar with laser pointers. So why am I trying to convince you that fiber lasers have an advantage? And in order to answer that question, we'll go to the next slide. Okay, so why fiber laser? And the reason is given here. First of all, when you're dealing with a high power laser, one of the difficulties is removing the heat from the laser. And in order to remove heat from a laser, what you really need is a large surface area compared to the volume of the laser. Now, a fiber has is a geometry of a very, very long string, sort of. So that gives you a very, very large surface area in comparison to the volume of the laser. For that reason, it is relatively easy to remove the heat that accumulates within the laser as opposed to other types of lasers. The other advantage is that a fiber laser gives you a rugged system. There's no, I'm sure many of you are familiar with lasers with mirrors and mirror alignment. There in fiber lasers, there are no cavity alignments necessary because everything is in fiber. And the other point is the excellent beam quality, which is determined by the fiber geometry. The geometry of the fiber itself determines an excellent beam quality, and therefore it's very, very simple relatively to get good beam quality. The other 2 points are also important. First of all, the fiber laser is compatible with fiber coupled diodes as pumps. So if some of you are familiar with how to pump different types of lasers, one of the difficulties is getting the pump light into the lasing media. And with fibers, it's relatively simple because the pumps are often fiber coupled, and you can easily splice fibers to fibers, and therefore you have the advantage of the ease of getting the pump power into the laser medium, which is the fiber. And the last thing, which is no less important, is the high efficiency. In many of the fiber lasers, one is able to get optical efficiency as high as 85%, which is of course very important, especially if we're trying to produce a high power laser. Okay, so we've what happened now? One moment. Okay, we're back. Okay, so what's the state of the art with fiber lasers today? Well, we'll talk about CW lasers. There are CW lasers up to 20 kilowatt single mode with high beam quality. These are lasers which can be purchased on the market. And there are multi-mode lasers with lower beam quality as high as 120 kilowatts, which is quite impressive. These numbers are very, very high, and these can give you many of the applications that we spoke about earlier. which can be done also at a distance, can be done with these lasers. Pulse lasers also have their peak powers as high as megawatts with nanosecond lasers, and the average powers can be as high as a kilowatt or so. Now, but most of the high power applications will be done with CW lasers, and for that you have to get to the very high multi kilowatts. So I hope I've convinced you that fiber lasers, we went from lasers to fiber lasers, so fiber lasers are okay, but why am I telling you about Raman fiber lasers? Of course, the numbers I gave you a moment ago, I just went back one slide, are not Raman fiber lasers. These are standard rare earth fiber lasers. And then the question would be, as I said, why am I trying to tell you a story about Raman fiber lasers, which have clearly not reached those levels? But I hope to convince you in this talk that they do have the potential of coming up to those sort of levels, and that's what the talk is going to be about. So first of all, I'm going to tell you what's the motivation for Raman fiber lasers. Why do I think that Raman fiber laser is a good direction to try to work? And then we'll talk about various Raman fiber laser pumping schemes, some results with Raman lasers, and then we will talk about the challenges and future directions which can be forecast for Raman fiber lasers. What does fiber laser look like? Well, the Raman fiber laser, the typical Raman fiber lasers, first of all, starts with the pump laser here on the left. The pump laser can be either a diode laser, or it can be a bulk laser, or it can be a fiber laser. It can be any of different types of lasers. Let me try to get that one second. Okay, once you have this pump, the pump is usually coupled into a fiber, and then what you have is a Raman laser. A Raman laser is usually just a Raman fiber, a certain fiber which has certain characteristics which allow it to produce the Raman wavelength, which we'll discuss in a moment, and a cavity, which is a high reflection mirror and a partial reflection mirror. Now, even though I mentioned earlier that there's no cavity in most fiber lasers, that's correct, because these mirrors are engraved directly on the fiber. So this just looks like a very long fiber with various components along the way. So like I said, there's no alignment necessary because it's all on the fiber, and of course you have an output unit. So again, this is what the fiber laser, a typical Raman fiber laser looks like. We have a pump here, and we have the sort of the cavity and the Raman fiber. So let's just give you a quick background of what is Raman scattering. The Raman effect was discovered in 1925 by Professor Rahman in India. And what it is basically, it's the ability, what here on the left here, look at the scheme, it occurs in any sort of, it occurs in many materials. It can happen in gases, in solids, in liquids. What it is you have a pump photon which hits the target, and then the molecule goes up to some virtual level, and then it comes back down, and a Raman photon is produced. Now, the Raman photon, in the cases that I'm going to be talking about, it's a Stokes photon, meaning that the wavelength is going to be longer, and of course the energy will be lower. Now, there's also some phonon heat which is left in the molecule or whatever the target material is. But what's very important here is this virtual level is not a real level, which means that you can basically do this with any wavelength. It doesn't have to be any specific wavelength because the material does not have to have any specific level, because this is a virtual level. And in any case, we pump it with a certain photon, and we get out a Raman photon which is wavelength shifted by a certain amount. Now, in a standard silica fiber, the peak shift is shifted by about 13 terahertz, which for example, if you pump with a 1070 nanometer pump, you're going to get shifted by about 50 nanometers. In other words, from 1070, you go to about 1120 nanometers, which is not a very significant not a very significant movement. What's important to notice is that we're not losing a lot of the amount of energy left in the target is not very high. So now the thing is like this. Here's what's interesting. At low intensities, the transfer efficiencies are very low, about 10 to the minus 6. But at high intensities, it turns into a stimulated effect, and the transfer efficiencies can reach as high as 90%. And now I'm going to tell you where we stand with. Now I'm going to go into why I think Raman has the ability to be a high power source. And I'm going to tell you a little bit about where conventional high power fiber laser sources are at right now. Conventional single mode fiber lasers, conventional ones. Okay, I told you earlier that there are 20 kilowatt single mode fiber lasers, but I'll get to that in a second. But conventional single mode fiber lasers have hit a certain barrier at the level of 3 to 4 kilowatts. Okay, now this barrier has been overcome by something called tandem pumping, and I'll explain that in a moment. But this solution for the problem has allowed powers as high as 20 kilowatts by IPG company and other companies, and I'll explain to you what exactly happened and how they managed to solve the problem. What you see here is a graph of the absorption cross section and the emission cross section of ytterbium, which is the standard fiber used for high power. Okay, what you can see is that it has a very strong absorption peak at about 975 nanometers, and for various reasons, the best place, in other words, in order to not have competition between the emission and the absorption, you don't want to have absorption, so you want to have an emission which is beyond the area where there is any significant absorption, and basically the most efficient type of laser is usually about 1080. So we're talking about pumping at about 980 and lasing at about 1080. So what happens? Oh, 1 second. Oh, okay. So that's the conventional. That is the conventional type of laser. Now, when I talk about tandem pumping means that there are 2 steps. Now, here are the 2 steps. First of all, we pump it with the same wavelength, but now we have a laser which lasers at about 1020, and now this 1020 is used to pump the next laser, which lasers at 1080. So instead of having the conventional laser pumped at 980 and lasing at 1080, we have pumping at 980 and lasing at 1080. We have a tandem pumping, which means we do it in 2 steps. We have a 980 which lasers at 1020, and the 1020 is a pump which lasers at 1080. Now, why is this an advantage? Why is having 2 steps an advantage? I'll explain it to you in a moment. If you see in the conventional, which is the green, the top one here, you see that the heat left in the fiber is the heat which is caused from the quantum defect between the 980 and the 1080, which is about 10% of the power, as opposed to the case of the tandem pumping. Here, the quantum defect of the second stage node is only 5%. Okay, now why is this good? Because that means that there's less heat left in the fiber. So here we have about 5% left in the fiber, as opposed to about 10% left in the fiber. Now note that this 2-step stage is not more efficient. I'm still starting at 980 and ending at 1080, but half of the heat is left in a different system. So in the fiber itself, which is of course the final fiber where the high power is being produced, there we have about half of the heat as opposed to the previous conventional case. So that's, as I said, so that tandem pumping solution allowed the lasers to go up from about 4 kilowatts to about 20 kilowatts, and that seems to be working fine. However, lasers are very sensitive. For example, the backscatter, and have therefore not gained popular use. For example, I did mention to you earlier that there are multi-mode lasers of up to 120 kilowatts. Now, these 120 kilowatt lasers usually use some sort of a combining. They use a combining of of some of the smaller lasers. Now, you would have expected, in order to make things simple, that they would be using the 20 kilowatt single mode to combine as few as possible to get as high as 120. But the fact is that they're really actually using the 1 to 3 kilowatts because the 20 kilowatts are very difficult to work with, and they're very sensitive. So therefore, as I said, even though they have reached the level of 20 kilowatts, there is still a certain problem with reaching those levels. So now I want to tell you, based on what we just said, so what are the advantages of Raman fiber laser as a high power source? First of all, what I've just mentioned, it has a low quantum defect, about 5%. This is similar to the tandem pumping solution, which allowed the various companies to reach the high 20 kilowatt lasers, as opposed to the conventional fiber lasers, which have about a 10% quantum defect of heat left in the fiber. Now, so now that we've finished that, I'm going to tell you a number of other advantages that Raman fiber lasers have as opposed to conventional fiber lasers. First of all, there are no rare earth doping in the fiber. And there's a certain problem with rare earth doping. On the standard fibers have photodarkening, which means that after a while, they start to lose their transmission. And that's a problem which is well known. And this problem does not exist in Raman fiber lasers because it's not rare earth, it's standard germanium doped fibers. The other advantage is that it has potential for wavelengths unavailable by other methods. Okay, I mentioned earlier by Raman, we're not limited to specific wavelengths of the material. We can work at Raman wavelengths. We have brightness enhancement. I'll talk about that later, but let me just mention it now. The signal has higher brightness than the pump source. And now another thing which is very important for those of you who are aware of problems with high power lasers is something to be called modal instability. This is believed to be the major obstacle to fiber laser power increase. Now, is under discussion in many of the scientific papers over the last few years, but the effect is connected to heat left in the fiber. And now, as we know, there's less heat. Because we spoke about the fact that there is less quantum defect. The other point is that the population inversion thermal gratings. This is another problem which causes the modal instability. This is not relevant in Raman. And others have connected the modal instability to photodarkening, which, as I mentioned, also is not relevant to Raman fibers. So for all these reasons, I believe that Raman fiber lasers has the potential to serve as a high power source. Okay, so now that I hope to convince you that Raman fiber lasers have potential to be high power sources, I want to tell you about different types of schemes, and I'll tell you what we're going to be talking about today. So first of all, there are three types of Raman fiber lasers. I mentioned to you that a typical fiber laser, the pump laser is fed into the fiber and into the Raman fiber, that is, into the cavity of the Raman fiber, and then from the other side we exit with the Raman wavelength. Now the question is, into what part of the fiber is the pump fed into? Now, one possibility is feeding it right into the core. Okay, in that case, the pump is in the core, and the Raman is generated in the core also. Now, what that means is there's no brightness enhancement because they're both in the same geometry. In order to get, as we spoke about earlier, the advantage of a good beam quality is the fact that it's in a smaller geometry. Okay, so in this case, if you want to make a 1 kilowatt Raman fiber laser, you basically need a 1.1 fiber laser to begin with. Means you're not really increasing the brightness, you're losing out on the brightness because of the 90% efficiency. So really, this is not something that the Raman contributes anything to producing a brighter source. Another type of pumping, which is similar to the type of pumping in conventional fiber lasers, what you do is the pump is inserted into the inner clad, which is of course a larger diameter than the core, and the Raman wavelength is generated in the core. In this case, you receive your brightness enhancement because now the signal is in a smaller geometry, meaning that it has better optical quality than the pump. That's the kind of thing we're looking for. And the third type of laser scheme that we're talking about is a graded index fiber. Here, once again, a graded index fiber usually is a multi-mode fiber. Say standard graded index is about 60 microns. Okay, so you put a pump into you feed a pump into about 60 microns into the large diameter. But what happens is the signal is generated in the center, and the reason and the way that this happens is because I said to you earlier that the Raman fiber is germanium doped, and a graded index fiber. What is a graded index fiber? In the center, it has a higher refractive index than on the peripheral areas of the fiber. So in the center, the Raman effect is stronger. So what occurs is that even though I feed the pump into the large diameter, the Raman is generated in the center and giving me brightness enhancement. So for that reason, the last two geometries are the ones that I'm going to be interested in. But just to mention it, the maximum prior power that was produced with the core pumping is close to 4 kilowatt. But I think that's going to be the last word I'm going to be saying about this geometry. From now until the end of the talk, I'm going to be only going to be talking about geometries which allow us to get brightness enhancement. Now we've been working on these issues here for about 5 years now. And before we started, the maximum power that was available with this geometry was about 100 watts, and the maximum power that was available with graded index fibers was about 20 watts. Since then, we were able to increase the powers in both of these geometries. We produced 1200 watts with an interclad geometry, and with the graded index we produced 150 watts. But the world doesn't wait for us, and there's another group actually in China which have also been working on this, and in the graded index fiber they have produced 2 kilowatts in this graded index. So this is just a synopsis of where the state of the art today. But I'm going to be telling you about how each of these steps were made and where it stands now. So it's like I said, the bottom line is that up to today, the highest power that was demonstrated with an interclad pump is about 1200 watts. That was done by us, and we published it in a year or two ago. And the highest power, which was demonstrated with graded index fiber, is about 2 kilowatts, and that was published actually just this year in 2020, a month or two ago. Okay, so let's talk about what is a Raman fiber. What does it look like? So I told you. So first of all, it could start. In this case, we're starting with the lower powers. It could start with a standard graded index fiber off the shelf from any fiber manufacturer. There was purchased from Thor Labs, and this is the heart of the system. But of course, you have to, in order to build a cavity, you need a mirror. In this case, we used bulk mirrors, not FPGs written on the fiber. So you see, we needed a lens to focus onto the mirror, and the front mirror. This was a high reflective mirror, and the front mirror was just a 4% Fresnel reflections. Now, the other thing we did here is this mirror here was not only a mirror for the Raman wavelength, it was also a mirror for the pump, which allowed the pump to make a second pass through the fiber. See, and the other thing which was important with this mirror is that it transmits the second strokes. Now, the second strokes is once you're using a pump and you get the first strokes. The first strokes can generate the second strokes. Of course, that is not desirable. So you would like to filter that out from the setup. Now, the other important point of this setup is, of course, the diodes. And the last thing, which is everything, which is going to be added on now, is just diagnostics. It actually starts with focusing from the pump into the fiber and diagnostics. So that's all. That's everything you see here. This is all as I said, focusing into the fiber and diagnostics. But the heart of the system is the cavity, which is here on the right, and on the left is the pump. Okay, now with this system, we were able to get about 150 watts with an efficiency of about 65%. In other words, when we put in about 240 watts, we were able to get 154 watts, which is very nice. As I said, when this work first started, the highest was 20 watt. But of course we want, and you can see, look what happened here. Look at the brightness enhancement. You see, this was the pump beam, and the Raman beam is of course much tighter, and therefore you can see the brightness enhancement. You can see the improvement in the optical quality of this beam. But if you take a good look at the results, you'll see. You look at this is a graph of the m squared that we got as a function of the power. You can see that the m squared started at about m squared 4, and slowly climbed up to a higher m squared of 8. Now m squared of 8 is let me just say what m squared means. Sure, most of you are familiar, but just in case, what you always like to get diffraction limit beam, which is somewhere around m squared of about 1.2, and as the m squared gets higher and higher, that means that your beam quality is deteriorating. So these results were nice power, but the beam quality still needs to be improved, and this is what we wanted to do. So these were our first results. They were encouraging, but we wanted to go on. So what are the limitations of the above scheme? First of all, we used bulk optics, mirrors. This is not ruggedizable. It's not like a fiber, like I was telling you earlier. So what should be done in order to improve this setup? And the answer, of course, is to use on-fiber FPGs. So that way we don't have to focus in and out of the fiber, and it's all in the fiber. And sure enough, in 2017, a group from Russia was able to write FPGs, fiber grading mirrors, on a green fiber, and they were able to demonstrate about 50 watts. Now, the power was not as high as we had demonstrated, but what's important here is you can see the m square it has been improved nicely, and they got an m square of about 2.6, which is of course a lot better than 8 that we showed earlier. But note that the efficiency is not very high; it was about 28%. But those were the results that they got. So what are the limitations of the above scheme? First of all, they I didn't mention it, but let me go back. They used, in order to pump the Raman laser, they were using diode pumped. They were using diode lasers that were pumping this laser, and diode pump lasers are very nice, but they have limited power and limited brightness. So what should we do in order to be able to increase the power and the brightness of the pump? Now, if you use fiber lasers, which have high power and medium brightness, again, not single mode, because if you're using single mode, then you're not going to get any brightness enhancement because there's nothing to improve. But if you use medium brightness fiber lasers, you can then improve the brightness and achieve with the Raman fiber lasers the high power and the good beam quality. So in this case, what we did is we actually did this work together with the Russian group. You can see here that they basically supplied us with the FPGs on the green fiber. That's the reason why it's not so simple to write fiber gradings on green fibers. On single mode fibers, it's quite easy. Many companies can do it, but the writing on a green fiber, which has a large diameter, is not so simple. In any case, this is what we did, and we were able to demonstrate 135 watts with 68% efficiency. And once again, the m square is reasonable at about 2.5. And what's also important to note is that you don't have that deterioration as the power goes up. You see here on this graph, you can see as the power increases, the blue line here is pretty steady, and it's stayed at an m square of about 2.5. Okay, so FPG mirrors are very good, but they have pros and cons. First of all, we said the advantages is that they're ruggedized and they sit on the fiber. but it and the other advantage is that it confines the laser to low fiber modes, so it provides reasonable beam quality even in the multi-mode fiber case, as we saw just before. However, FPGs may be limited in sustaining high power, and in order to try to improve the results here, there's a possibility of using an amplifier configuration instead of a cavity. And here's a work by a Chinese group, and what they did is they took a seed laser and they amplified. Here, there's no cavity. There are no FPG mirrors on this setup. They just feed it into the Raman fiber, and the Raman fiber was pumped by fiber laser, and they were able to achieve a kilowatt with this setup. This was done. This was done in last year, and I think M square is not. So these were their results. And then actually, this is the work that I mentioned to you earlier. They continued to improve, and they actually got as high as 2 kilowatts with a very similar setup. They have a seeder, and they feed it into the Raman fiber. They pump the Raman fiber with the fiber laser. But once again, they got 2 kilowatts, but the M square is not very good. As a matter of fact, they did not achieve brightness enhancement. They actually lost the brightness. But this just shows that that such power levels are possible with these levels. Now, but so that's nice if you have high power levels. But if you also want to have high power levels with improved beam quality, you need larger fibers which can accommodate the high powers. But what you're going to have to go in the direction of interclad pumping, which I mentioned to you earlier. In other words, where you pump with, up to now I was talking about multi-mode graded index fibers. Okay, here I'm talking about interclad pumping, meaning the pump is fed into the clad, the interclad of the fiber. It is, for example, in a double clad fiber, or actually a triple clad fibers, and then the Raman is generated in the core. Now there is an issue. I'm not going to talk about it too much, but there is a geometrical characteristic that has to be kept. You need a low clad to core diameter ratio in order to prevent the second Stokes from being generated. So you basically need a specially designed fiber, and this is what we did here in this case. We designed a special fiber. The fiber had a 25 micron core, a 45 micron inner clad, and the outer clad was about 250 microns, but that's not relevant because the pump was introduced into the 45 micron inner clad. And these were our first results with this fiber. We basically we combined a few fiber lasers. These are a few fiber lasers, which each of them was single mode, but together combined, they are no longer single mode, because of combining, you're always going to lose some brightness when you combine a number of sources. And what you have here is the fiber itself, this triple clad fiber, which was 160 meters long, and you have a mirror on each side of the fiber, which was written directly on the fiber. In this case, we achieved about 250 watts with 60% efficiency, with an M squared, which is considerably better than the other results they were getting, but it's not as good as we would like it to be. In our continuation of this same work, we were able to increase the power. And here, once again, we used the same triple clad fiber. Again, we combined a number of fiber lasers, and these were generated. These were fed into the Raman fiber, and there were mirrors on the edges of two sides of the fiber. And as you can see, we reached a level of 1200 watts, and with an efficiency of about 85%. Let's see. And here you can see the M square. The M square is about 2.75 at a level of 1 kilowatt. So this is already, as I said, a kilowatt with M squared in the area of about 2. Not as good as we would like it to be, but it's going in the right direction. Now this I'm showing you now. So now here, up till now, one second, I was telling you about our work. Now here, here's a paper that was published this month, actually, in 2020, where another Chinese group did. They also used a triple clad fiber, and they used an amplifier configuration. So they were able to show up to 760 watts. Their efficiency was not high, and that's a problem with amplification. Amplifiers generally have lower efficiency, especially if the seed laser is not very strong. But they were able to get a very, very nice M square. So you can see that the direction here of going into a high power with low M square, meaning good quality, is something which is going in the right direction. So I'm towards the end of my presentation. I just want to give you a quick summary of what we saw. So what are the limiting factors for further increase to higher power with good beam quality? Well, we saw that the grid fibers usually showed low power or poor beam quality. For example, with FPGs, excuse me, the power was limited to about under 200 watts, even though the beam quality was reasonable. But without FPGs, you saw that they were able to get as high as 2 kilowatts, but the M squared, the beam quality was quite poor. On the other hand, the multi-clad fibers, or the clad fibers, seem to be the best option at this point. Both lasers and amplifier configurations have reached almost the kilowatt level with M squared, which is lower than 3, which gives us, which of course seems like this is the right direction. Now the optical efficiency of the laser was about 85% in the work that we showed at 1200 watts. In the amplifier, the efficiency is still quite low, but this seems to be the right direction. So what's left to be done? We need to improve the fiber design to get better beam quality. We want to get as low as possible, under M squared of 2. Today we're about 2.7, 2.5. And another thing which I didn't mention up till now, but it's something which has to be dealt with, is the need to filter out the backscatter for the Raman laser. The Raman laser is connected directly to the pump of the pump laser, and some of this the light from the Raman laser can be fed back into the pump laser, which can cause instabilities in the pump laser. So here are basically my conclusions. The Raman fiber lasers has potential to serve as high power, high brightness fiber laser alternative, and Raman lasers have shown to allow kilowatt level lasers without rare earth doping fibers. Therefore, there's less required heat removal, there's less photo darkening, and there's less modal instability. There is room, of course, for further improvements, improve the fiber design and to block back scatter to pumps. I'd like to thank you very much for staying with me. And I think now that we're open for questions. Let's see if I can. I don't know if people are asking questions because I don't see the, well, you're supposed to ask questions on the question and answer sheet, but I don't know where that is. Okay, if the technical staff wants to help me out on that, I wouldn't mind.
No. כן, כן, זאת המטרה שלי לגמרי. זהו, אני אשמח שתשלחי לי.
Okay, I can hear you, but I don't see the question and answer sheet, so
I can read for you the question. One question is Raman laser able to cut bronze, brass, and aluminum in the same quality and thickness?
Oh, what determines the ability to cut into a metal is basically the power and the beam quality. Those are the two most important characteristics, and therefore, as I said, the Raman fiber lasers have not reached the level of conventional lasers yet. But when they do, there won't be much of a difference between their performance and the performance of the conventional lasers. So that would be, I mean, so the wavelength. The difference in wavelength is not very significant. I mean, of course, there are always optimizations that can be done, but in principle, there shouldn't be any principal difference between Raman lasers and conventional lasers.
Another question is, I assume this fiber is the most expensive component in the system. How much long I can use it if it is work 24/7?
That question is a good question, and it's the same question you would ask any fiber laser manufacturer. And my answer is, as I mentioned to you earlier, since some of the things that cause the shortening life in conventional lasers, such as photo darkening well, mostly photo darkening, I would say. That's something which limits the life of conventional fiber lasers. I would say that there's no reason why the fiber laser should have a shorter life, and actually just the opposite. I would assume that a fiber laser, as I said, it's a regular germanium doped fiber, and therefore I don't think it should have any shorter life, and the components are compatible with regular fibers. There's basically no difference between the fiber lasers and the Raman fiber lasers, except for the fact that the fiber itself is not rare earth doped, and that solves you many problems in comparison to general fiber lasers.
Okay, any more questions? I don't see it on the Q&A, but verbally, if someone wants to ask questions. If not, I would like to thank you, Dr. Glik, and for this interesting lecture.
Okay. Thank you.
Thank you very much.